Good morning friends. Today we will discuss about the kinetic theory of gases. This topic is a kinetic theory of gases and not the kinetic theory of solid and liquid. Actually there are three states of matter: solid, liquid and gases. There is a basic difference between the solid, liquid and gases is, in case of solid the force of attraction between the molecules is strong. In case of liquid the force of attraction between the molecules, that is molecular force of attraction, is small as compared to the solid but greater than that in case of the gas. Whereas the force of attraction between the molecules, that is molecular force of attraction, in case of gas is very small, or we can say negligible as compared to solid, liquid and gases. Second difference is, in case of solid the atoms or molecules are closely or tightly bounded. In case of liquid these molecules are weakly bounded as compared to the solid, but they are tightly bounded as compared to the gas. Whereas in case of gas, these molecules or atoms are very loosely bounded. It means that the force of attraction is very small, means negligible as compared to the solid and liquid. In this topic we have to discuss the kinetic theory of gases. Why we discuss only the kinetic theory of gases and not the solid and liquid? The reason is that if we take same amount of solid, liquid and gas, and if we heat solid, liquid and gas of same amount at a particular temperature, then we will observe that for, we can say, or for example, for 1 degree of Celsius of temperature, there is no change in the pressure or volume in case of gas. There is no change in pressure or volume in case of solid and liquid. But there is a tremendous change in the pressure and volume of gas for 1 degree Celsius of temperature. And due to this, the kinetic energy of molecules changes, and that's why we have to study about the kinetic theory of gases. Now there are three gas laws. These three gas laws are nothing but: number one, Boyle's law. This Boyle's law states that the pressure of a gas containing in a vessel is inversely proportional to the volume. This pressure is inversely proportional to volume, keeping the constant temperature, means at constant temperature. This is nothing but Boyle's law. Second is Charles' law. Second gas law is Charles' law. This Charles' law states that the volume occupied by the gas in a container is directly proportional to the temperature at constant pressure. And third is Gay-Lussac's law. Gay-Lussac's law. This Gay-Lussac's law states that the pressure of the gas in a container is directly proportional to the temperature, that is pressure directly proportional to temperature at constant volume. In this way there are three gas laws. So P inversely proportional to V, V directly proportional to T, T directly proportional to T. Now after combining any two equations of these three equations, we get, suppose this is equation 2, means this is first, second, third, and after combining second and third, 2 and 3, we get PV proportional to T. P into V directly proportional to T. It means that PV is equal to RT, where R is constant and therefore this constant R is called universal gas constant. The value of this universal gas constant is 8.13 or 8.314 joule per mole per Kelvin. This is the value of universal gas constant, and this is for 1 mole of gas. Now, for n mole of gas, PV is equal to nRT. This is called gas equation or ideal gas equation. This equation is also called gas equation or ideal gas equation, and therefore PV, or we can write P1 V1 is equal to, or P1 V1 upon P2 V2 is equal to T1 upon T2. This is nothing but ideal gas equation or condition of gas equation. Here n is equal to number of mole of gas, and this number of mole of gas is nothing but n is equal to mass of gas in gram upon its molar mass or molecular weight, or number of molecules upon Avogadro's number, and therefore we can define the number of moles is equal to the ratio of mass of gas to the molar mass of gas, or the number of molecules in a gas to the ratio of molecular number of molecules of gas to the Avogadro's number. Here we have seen that R is universal gas constant. Then we can see the relation between number of molecules and universal gas constant, that is R and N, that is R is equal to N A into K beta, where, sorry, not N A, only N into K beta, where K beta is Boltzmann constant. Boltzmann constant, and therefore this equation PV is equal to nRT can be written as PV is equal to N into N K beta into T. Here this R is equal to not N K beta, N A K beta T, and therefore we can write N A K beta T. Therefore this can be written as N into Na, means N into Na is equal to N K beta into T. This is what is ideal gas equation? A gas obeying the equation of state, that is PV is equal to nRT. This equation is also called the equation of state. PV is equal to nRT. Means a gas which obeys the equation of state, that is PV is equal to nRT, at all pressure and temperature is called ideal gas. Means this gas obeys this equation at all pressure and temperature. No other gas obeys this equation at all pressure and temperature, and therefore ideal gas cannot be exist in nature. Now we can see ideal gas in terms of density of gas. Ideal gas in terms of density of gas. So using PV is equal to nRT, means PV is equal to m upon m0 into RT. This can be written as P is equal to m upon V into RT upon m0. This we can be written in divider or denominator, and therefore P is equal to rho into RT upon m0, where rho is equal to mass upon volume, that is the density of gas, and hence the pressure of gas can be defined as, or can be stated as, P is equal to rho into R into T upon m0. Now we see ideal gas and real gas. As we have seen, ideal gas, a gas which obeys the gas equation PV is equal to nRT at all temperature and pressure is called ideal gas. Or in other words, we can define a gas which satisfies all the assumptions of kinetic theory of gases. Means there are some assumptions of kinetic theory of gases to explain the gas equation or the behavior of gas. So a gas which satisfies all the assumptions of kinetic theory of gases at all temperature and pressure is known as ideal gas. Second point is ideal gas cannot be liquefied or it cannot be solidified easily also. Intermolecular force of attraction or repulsion in case of ideal gas is 0 except during the collision. Means in case of collision there is a force of attraction, but without collision the intermolecular force of attraction between the ideal gas molecules is 0. Second is real gas. Real gas means a gas which satisfies all the conditions of assumptions of kinetic theory of gases at high temperature and low pressure. Means a gas which satisfies the assumptions of kinetic theory of gases at high temperature and low pressure is called real gas. Real gas can be liquefied under certain conditions. Now at very high temperature and low pressure, real gas obeys ideal gas. If we change the condition of gas, that is high temperature and low pressure, then this real gas can also behave like ideal gas. After this, we see the mean free path. Mean free path. So what is free path and what is According to the kinetic theory of gases or according to the assumptions of kinetic theory of gases, the gases or molecules of gas are continuously in the state of random motion. Means suppose this molecule move to this, then it move to this, then it move here, then it move here, then it reach to this, then it move. Means in this way. There are different ways, path. Molecules of gas can be traveled. During this motion, they collide with each other, and during this collision, these molecules travels a distance. So, the distance traveled by the molecule between successive collision is called free path. Means first we see free path. So, what is free path? The distance traveled by molecule between successive collision is called free path. Now we have to define mean free path. Mean free path. It is denoted by lambda. In this term, there is a mean, means mean of free path. So, the average distance traveled, the average distance traveled by molecule between two successive collision is called mean free path. This mean free path is denoted by lambda, and therefore we can write this lambda is equal to 1 upon under root 2 pi into d square into n by v, where this n by v is nothing but the number of molecules upon volume, that is volume density. So this can be written as 1 upon under root 2 pi into d square v, that is volume rho, that is volume density, and this is nothing but mean free path. Now we term or we define some basic terms of kinetic theory of gases. Now we see some basic terms about the kinetic theory of gases. So consider n molecules of gas in a container are continuously in the random motion, and they are moving with speeds c1, c2, c3, c4 up to cn. Means these are the speeds of n molecules of gas. So first we see mean velocity of gas molecules. So it is the mean of the velocity, and therefore we can define as the average of the velocities of n molecules of gas is called mean velocity of gas. It is denoted by c bar. This bar indicates that the mean of velocities, and therefore we can write c1 plus c2 plus c3 plus up to cn divided by n. Means this is nothing but the average of velocities of n molecules of gas. Its SI unit is meter per second. Second gases. In the next lecture, we will discuss the pressure exerted by gas, or we will derive an expression for the pressure exerted by the gas.